Hello everyone, I welcome you all to today's class. In this entire lecture series, we will be covering all the fundamental aspects of heat transfer. So let's get started. What is heat transfer? Let's start with the definition, right? What do you think? What is heat transfer? Heat transfer is nothing but the transfer of heat. But will there be transfer of heat all the time? Is there any condition behind the transfer of heat? Yes, there is a condition, and the condition is the temperature difference that will act as the driving force of heat transfer. For example, suppose this is a metallic rod and I am trying to heat this part. Okay, so there is a heat source here, and because of this heat source, suppose I am lighting up a candle here, so this part will become hot with the passage of time. This part will be hot, and as this part is getting hot, that means that rise in temperature is observed here. So we see that this heat is conducted to this region where there is no heat source. That means this part is having a lower temperature. So this part having higher temperature, this part having a lower temperature. What is temperature? Temperature is the measurement of heat. That means this part is more hot than this part, right? So this phenomenon is called the conduction of heat. So because the heat is conducting from this part to this part. So this is a classic example of heat transfer, and this is conduction mode of heat transfer. Okay, so there are basically three types of three modes of heat transfer. Okay, so let me write it down here. Modes of HT, that means modes of heat transfer. You will find three modes of heat transfer. One is conduction, then convection, and the third one is radiation. These are the three modes of heat transfer, and we will discuss about all of the modes in very much detail, and we'll also solve the numericals that can be asked in your BTech courses or even your MTech or higher engineering courses. Okay, so this slide describes the definition of heat transfer. What is heat transfer? The science that deals with the determination of the rates of energy transfer due to the temperature difference is the heat transfer, right? Transfer of heat from one region to other by the virtue of the temperature difference between them. What is the driving force? I have already mentioned that is the temperature difference, as the voltage difference in electric current, as the pressure difference in fluid flow, right? Why will be there fluid flow? Right, if there is no pressure difference, there will be no fluid flow. That means the pressure difference is the driving force for the fluid flow, right? And the rate of the heat transfer will depend on the magnitude of the delta T. Delta T means the difference of the temperature, right? The example that I had given you earlier, I will explain it in more brief manner in our upcoming slides. Okay, so what are the different application areas of heat transfer, where we see them and where we see them in action in real life? Just today, when you had your cup of coffee or cup of tea, you may have noticed that it is getting colder with the passage of time, right? Why? Because the temperature of the cup of coffee is higher than that of the ambient, right? So that is why there is a convection mode of heat transfer. We will discuss about all the modes in brief manner. There can be heat transfer in the air conditioners, in the refrigerators, in the radiators, in the heat exchangers, right? So these are the different application areas of heat transfer. Nowadays, we also see different research papers on the Peltier modules, right? The Peltier modules, the thermoelectric coolers, they are being also used, and we can also have the coefficient of performance of the cooling performance, of the heating performance of them, and these are also the classic examples of heat transfer. All right, let's move forward and see the differences between thermodynamics and heat transfer. So what is the basic difference between them? See, thermodynamics only deals with the amount of energy. The energy can be heat or work during a process. Thermodynamics deals with the amount of energy during a process. Okay. On the other hand, heat transfer deals with the rate of energy transfer. With one word, you will understand it very clearly. In thermodynamics, you had different formulas for different processes. In thermodynamics, we typically have four processes, right? isothermal process, adiabatic process, isobaric process, and isochoric process. Although in isochoric process, the volume remains same, the volume remains constant. That is why there is no work. But in isothermal process, in adiabatic process, in isobaric process, in the other three processes, what you get is some amount of work, and the unit of work is what? The unit of work is simply joule, 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 right? The unit of work is joule. Let me just remind you the formulas that you have already studied. This is my note. You can just take a look from here. See, this is isothermal process, the heading isothermal process. In the isothermal process, if you just derive the formula, in isothermal process, the temperature will remain constant. Iso means same. Thermal is related to temperature. That means the temperature will remain constant. And in the gas laws, we have already studied that Boyle's law is the law where the temperature will remain constant. That means PV equal to constant. P means pressure, V means volume. So by using this and some calculations, we get the equation for the work done in constant temperature process, and that is P1 V1 ln V2 over V1. Okay, here V2 you can see V2 is the final temperature, final volume, and V1 will be the initial volume, right? So like this, and then you can also modify it P1 V1 ln P1 over P2, or P2 V2 ln P1 over P2. So these are the equations of the work done in case of isothermal process. Like this, you will also get work done equation in case of adiabatic process and isobaric process. So what is the equation? What is the unit for work? That is joule. That is joule. That means these works that you have all found are joules, right? Now here comes the twist. Heat transfer will deal with the rate of energy transfer. That means it will deal with the what. What means joule per second. What means joule per second? And in thermodynamics, we are only concerned about joules. And in case of heat transfer, we are concerned about joule per second. That means the rate of the energy transfer. You were not calculating the rate of the energy transfer from one state to the other state in case of a thermodynamic process, right? You were only concerned about the work. Joule, in joule you figured out the values. In case of adiabatic process, you can also see you had equations, you had derived different equations. See here, adiabatic process. In adiabatic process, in your work done equation is P2 V2 minus P1 V1 1 minus gamma. This is the equation. So, and in case of isobaric process, that is PdV, right? So all of the equations, all of the units of this work done are in joule. But in case of heat transfer, you are also concerned about the rate of the heat transfer, that how the heat is transferred from one point to the other and what is the rate, right? So this is the subsequent difference between these two, thermodynamics and heat transfer. We have to be aware of this. In thermodynamics, we were only concerned about the equilibrium states. We considered all the states in equilibrium. And now you may ask that what is state, what is property? I will just give you an overview of that as well. See, see this. Take a look at this state diagram. I want you to take a look at this state diagram. See, this is pressure and this is volume, and this is 1 and this is 2. So this point 1 is state 1, this point 2 is state 2, right? And this state is being represented by the property. Here you can see condition of the state system, condition of the system represented by its property can be called as the state. Okay, and property is the characteristic of the system which represents the state of the system. Okay, so you can see that pressure, volume, temperature, moles, these are the properties. On the other hand, by using these properties, you are actually determining the conditions, right? State 1 is having some pressure P1 and some volume, that is V1. State 2 is also having some kind of pressure and some volume. That means the state is required some properties to be represented, right? So yeah, now let's go back to this slide and let's study about the most important thing we have studied, that in thermodynamics we only considered the states in the equilibrium. They were the equilibrium states. Now there are different equilibrium conditions in thermodynamics. We have already saw. See, to take a look at this first thing. You can see this is my own note. when I was a student of the third sem. I took this. So in equilibrium, there are mechanical equilibrium, chemical equilibrium, thermal equilibrium, thermodynamic equilibrium, right? So we considered the states in the equilibrium when we studied thermodynamics. But in case of heat transfer, we will not consider it in the equilibrium state. Okay, it can be non-equilibrium, it can also be transient. Okay, okay, and these are the most important differences we have already discussed about. Okay, it is a very important note that can be asked to you in your viva. Okay, the teachers like to ask these questions, and even in the uh, interviews of your job in a technical positions, you may be asked about this question. My own teacher, Dr. Ravinder Kumar, he also just shared me that he was asked this question, this very question, when he sat for the job interview. Okay, so that what is the basic difference between the thermodynamics and the heat transfer? We need to be aware that what I just told you, if you just say, I think it will be enough for the basic understanding. And thermodynamics will answer us why, and heat transfer will answer us how long. Like for how long there will be the transfer of heat, as the time is also concerned. Time is also taken into our account. Okay, so yeah, let's move forward. I hope that you understood it very clearly. Okay. So you see that in thermodynamics we had different laws. The zeroth law that is given by R.H. Fowler. Okay, that talks about the equilibrium of the temperature. I'm not going to go to in very detail. The uh, uh, first law that actually is concerned about the conservation of energy in case of thermodynamics. The second law talks about entropy, right? Like this, in laws of heat transfer, in case of conduction, we'll have Fourier law of heat conduction. Okay, in case of convection, we'll have the Newton's law of cooling in case of convection, and in case of radiation, we'll have Stephen Boltzmann law. Okay, we will discuss about all of them in very much detail. So what is the history of heat transfer? In the 18th century, too much way before, they thought that heat is a fluid like substance. They considered the heat like fluid. But nowadays, when you want to study fluid mechanics, you don't define fluid like this, right? Fluid is that which gets constantly deformed under the tangential stress, right? And now they actually in the 18th century thought that heat is fluid like substance, and it is caloric. Caloric, what does caloric mean? Caloric means it will be massless, it will be orderless, it will be tasteless, like this. And they say that it's poured from one body to the other body. Like if you consider this almost pink color a thing like hot body, and the other part is the cold body, the caloric fluid like substance will be poured from the hot body to the cold body, like this thing. Okay, let's discuss about heat, rate, and flux. These are very important terms. What is heat? Heat is the amount of heat transferred during a process. Heat transfer rate, the amount of heat transferred per unit time. When we say rate, we are generally concerned about the time, right? Sometimes also the rate can be expressed in terms of the length. That is very interesting. We can also see that. And heat flux, the rate of the heat transfer per unit area normal to the direction of the heat transfer. It is very interesting to see. Okay, it can be like this. Suppose this is a concrete slab. Okay, this is nothing but a concrete slab, and this area, that is area, and this is having some thickness dx. Okay, so this area, this is the hatched portion is the area, and there is heat like this. Okay, so what you know, you can say it like this. Okay, if that is q, this q will be equal to total heat divided by the area that it is normal to the action. Like say, for if this is the slab, if this is the concrete slab, and this is the heat, that is like this, normal to the area. Okay, and if this is the total amount of heat, what will be the heat flux? The heat flux will be this q divided by the area. That will give you the heat flux, right? You can understand it from here. And you can very easily understand from here that if the area is given as 6 meter per square, and q, the total heat right? That is given as 24 watt. 24 watt. What means joule per second? That means 24 joule per second is the heat transfer rate. And if you were asked to find the heat flux, you know that this is 24 divided by 6. Why? Because this is capital Q over area that it is perpendicular to the action, like this. Okay, you can understand it, right? So now we will study the conduction mode of heat transfer in a more brief manner. Okay, now let me give you, yeah, you can see this is mode of heat transfer, conduction. Okay, so there are different modes. I have already talked about conduction, convection, and radiation. See, in case of conduction, heat is always transferred by conduction from high temperature region to low temperature region. The conduction heat transfer is due to the property of matter and molecular transport of heat between two regions due to temperature difference. We have already talked about this. But when there will be conduction, when the material is same, like within this same material, if it is a rod, if it is a metallic rod, within this same material, from this point to this point, there will be conduction of heat, right? Or it can also be a stationary fluid. In a stationary fluid, from point A to point B, suppose for example, suppose it has a fluid inside of it. It has a fluid inside of it, and inside of it, from point A to point B, the heat is being conducted, right? Because it is a stationary fluid, and it is also conduction within this fluid from this point to this point, to this point, to this point, and different other points. There are conductions of heat. In which mechanism we will talk about this, that how the heat is actually conducted from this point to this point. We'll talk about that. But in a stationary fluid, there can also be conduction. It's not always in the metallic rods or something like that. Okay. See, this is this part. We are heating this portion. So suppose this is having temperature T1. This is having temperature T1, and this is having temperature T2. And we can say that T1 is greater than T2. That means there will be flow of heat from T1 to T2, right? T1 to T2, there will be flow of heat. Okay, so Q is flowing from here to here, right? This Q is joule per second. That means per unit time. It's already mentioned, right? All right. Now take a look at these parts, right? Why? How this actually is conducted? What is the mechanism? Mechanism is atomic vibration and the transport of the free electrons. The faster moving vibrating atoms in the hot area transfer heat to the adjacent atoms. You can understand it like this, that from this picture. Okay, so this molecule, as it is absorbing the heat, okay, it is getting excited and it is starting vibration on its own place. It's not moving from one part to the other. It is starting to vibrate, and as it has started vibrating, it will also vibrate its colleague molecule that is colored in red. Sorry, if that part, okay, this part is colored in red, so this part will also vibrate, right? So the blue molecule has started vibrating, and as it has started vibrating, it has also started or initiated some vibration to the colleague molecule, and the colleague molecule is also vibrating like this. From this part, if I want to take another color, the green portion, the green atom, that is vibrated like this. The heat is transferred from T1 region to the T2 region. You can understand that. From, I can say that, A region to B region, the heat is transferred like this. So this is a theory. This can also be be called as the atomic vibration theory, atomic mechanical vibration theory, right? This is how the atoms vibrate on its own place, thus conducting the heat from the higher temperature region to the lower temperature region. Now, when these two regions will come to an equilibrium, when they will come to an equilibrium of temperature, there will be no heat transfer anymore, right? You can understand it. Okay, because delta T, the difference of temperature, is the driving force for the conduction. All right. Now, there can also be the transport of free electrons. In metals, we know that there are a sea of free electrons, right? And those free electrons can transport the heat from point 1 to point 2, from the higher temperature region to the lower temperature region, like this. Okay. Now, you can study this. Okay, so now we'll study about the Fourier law of conduction. We have already seen that in case of conduction we have the Fourier law of conduction. Now say with me, in case of conduction we have Fourier law of conduction. In case of convection, what we have? Newton's law of cooling. In case of radiation, what we have? Boltzmann's law. Okay, we will already study all of them one by one. Now we will see the theoretic experimental. This formula actually is given by Fourier, and it is experimental. It has no proof, so you don't have to derive anything from here. Now let's study the Fourier law of heat conduction. Okay, so for that, let's take a look at figure 1.2. So this is basically a plain wall or slab like this. Okay, like this, a plain wall or slab. You can consider it like this. So it has two planes. I will just assume that this plane is having temperature T1 and this plane is having temperature T2, and at this plane where the temperature is T1, I am having a flow of heat. Okay, flow of heat like this. Okay, so this is the heat Q that is on it, that is perpendicular to the surface area. You can see perpendicular to the surface area there is a flow of heat, okay, in joule per second, in watt. This is Q. Okay, so this part is having temperature T1 and this is the isothermal plane. And now what do I mean by isothermal plane? Isothermal plane means that it is having T1 temperature throughout. That means at this point the temperature is T1, at this point the temperature is also T1, at this point the temperature is also T1. The temperature is not random. It's not randomly varying at different points. It's same throughout the plane. This is why this plane is known as the, or called as the isothermal plane. Like this other plane is also isothermal plane. So this one is having T1 temperature, this one is having T2 temperature, and it is having a heat source, right? It is having a flow of heat. That is, the flow of heat is perpendicular to the surface area, right? So that is why this will have a higher temperature region compared to this part. Okay, this is T2 and this is T1. This is T2, this is T1. So T1 is having higher temperature. That means from this picture I can say that T1 is greater than that of T2. So there will be a flow of heat from T1 to T2. From T1 to T2, you can see the flow of heat or the conduction of heat. The conduction process is taking place here. Why the conduction is taking place? Why not convection? Why not radiation? Although I haven't defined the convection and radiation, but in conduction it happens in the same material, within the same material or in stationary fluids, right? So you can understand that this is conduction. So from T1 to T1 there is conduction of heat. So from here you can see the Q, and this Q is directly perpendicular to the surface area here, right? You can see here, see from the figure. And dt is the temperature difference. Temperature difference means T2 minus T1. dt means what is the meaning of dt? That is T2 minus T1. Now can you observe one thing, that T2 is less than that of T1. From here T2 is less than that of T1. That means T2 minus T1 will be a negative number. It will be a negative number, right? Okay, for now let's just keep this in our mind. So, and the thickness of this slab or wall slab is plain wall or slab is dx. Thickness is dx. From the picture you can see this thickness is dx. Okay, and the dt is the temperature difference, and here you can see T1, here you can see the T2. Okay, so from T1 to T1 there is a conduction of heat, and Q1 from Q is conducted. The flow of heat is conducted from the higher temperature region to the lower temperature region. So this schematic is understood by us, and we also have understood that all the planes on which the heat is acting on are isothermal planes. Okay, so now this Q will depend on two things here. This Q will depend on two things, and Fourier law of heat conduction is not having any generalized derivation. It is based on some experimental evidences. Okay, like this, that Q is proportional to the area. Proportional to the area means that surface area on which this Q is flowing, like this, perpendicular to this surface area. So this Q is proportional to that surface area, and also this Q is proportional to dt dx. dt is the temperature difference, dx is the thickness of this slab. So that dt dx is the temperature gradient. dt dx is the temperature gradient. So now if I try to combine these two equations in one place. Okay, so I can write that Q, I can write that this Q is proportional to A dt dx. This is very easy, right? And now, in order to get rid of this proportionality sign, what do we do? In order to get rid of any proportionality sign, we bring a constant into the equation, and this is going to be like this: Q is equal to K. This is small k A dx, and this small k is our constant of proportionality. This is also a thermophysical property, and this is known as thermal conductivity. Okay, this k is the proportionality of constant of proportionality, thermophysical property, and you can also name it the thermal conductivity. Very important parameter in this equation here, right? What is the A? A is that surface area, dt is the temperature difference, and dx is the thickness of the plane wall or the slab. So, or dt over dx combinedly is called the temperature gradient, right? So this equation you can see over here is the Fourier law of heat conduction. Fourier law of heat conduction. Okay, so see Q is the heat conducted in watts, and watts means basically joule per second. That means it is actually referring the transfer of heat in terms of a second. That means the rate of transfer of heat, right? Okay. A is the surface area of heat flow in meter square. Surface area of the heat flow. Of course, it should be in meter square. So because the area are having two a length and the breadth, so it will be in meter square or in centimeter square or in millimeter square. We can convert and take according to our requirement, and that is perpendicular to the direction of the heat flow. That means this area is the perpendicular to the direction of the heat flow. dt is the temperature difference between the faces of the slab in degrees Celsius or Kelvin, and dx is the thickness of the slab in meter. So they have taken all the units in SI System Internationals. Okay. Now, one thing that may confuse you, or you may think that did they write it mistakenly, that Q is equal to negative Ka dt dx. Why this negative is coming in this equation? That is because I have already told you in the beginning that dt is the difference of temperature, T2 minus T1. dt is equal to T2 minus T1, because the difference we all in generally measure final minus initial. That gives us the difference. So this is negative because T2 is less than that of T1. T1 is having a higher temperature because in T1 there is the heat source or the flow of heat, right? So T1 is greater than T2. That means T2 is less than T1. So that is why the difference of the temperatures, or dt, is a negative value. And in order to compensate that negative value, here look at this dt. This dt is a negative value. So in order to compensate with this negative sign, they have brought another negative sign in this equation. So they both will cancel themselves, and they will provide you answer of Q in positive, right? It should be there. So you will get positive Q answers. But in case of the temperature gradient dt dx, in some questions you will be asked to find out the temperature gradient. So in those cases, if you want to find them, you will find the temperature gradient in negative. Why? Because dt is a negative number. T2 minus T1, that is a negative number. So temperature gradient is negative. That's okay. Okay, so here dt is negative because they have elaborated the reason why it is done. And now we want to talk about the thermal conductivity of this material, that is K. Okay, so if you look at this equation, Q is equal to K A T1 minus T2 divided by dx. Now you can see that if you write T2 minus T1 here, then you will need to put this negative sign. But here, if you already write T1 minus T2, that means you don't require the negative sign in front of this equation, in front of K, because T1 is greater than T2, right? So you can adjust it accordingly. No issues with that. So K is equal to Q dx over A T1 minus T2. We are just rearranging it in order to get the unit. Okay. So and then dx is there here. So A dt over dx, and then Q, the unit of heat is watt, and A is meter square, dt, difference of temperature, that is in degrees Celsius. It can also be in Kelvin, and dx is in meter, that is the thickness of the slab. So you find that K is having the unit as watt per meter into degree Celsius. Watt per meter into degree Celsius. So this is the unit of the K. And you can also define the thermal conductivity K of a material. It is a thermophysical property which is defined as the heat conducted through a body of unit area and unit thickness in unit time with unit temperature difference. You can say this from here as well. From here as well, K is equal to W. When the M is equal to 1, degree Celsius is equal to 1. It will be better if you provide the definition from here as well. From here, that K is equal to Q when dx is equal to 1 and A is equal to 1, T1 minus T2 is equal to 1, and also you take the consideration of time, unit time is also taken into consideration. Why? Because this Q already comes with time, like what already comes with what? Joule per second. So that means if you are saying that this K is equal to watt is equal to joule, that means you also have to keep this S is equal to 1. I don't know whether you can understand it or not. Like I'm just trying to have the definition from the equation. From the equation, you can also have definitions in sometimes. Okay. So yeah, this is how you can have the definition of the thermal conductivity. Okay. So now I want to provide you a brief overview of the assumptions that are taken when we are talking about the Fourier's law. Conduction of the heat takes place under steady state conditions. Okay, steady state condition. So steady state condition means that it is having no variation with time. The temperature is having conduction of heat takes under steady state conditions. Okay, so the heat flow is unidirectional. The direction is, this is the unidirectional heat. Okay, so it is not having bidirectional heat like from this part and as well as this part, bidirectional heat or tridirectional complex direction systems are not there. So it is only applicable in case of the unidirectional heats. Okay, the temperature gradient is constant. That means the dt dx, this is equal to a constant. The gradient should be constant. It is an assumption that they have taken, and the temperature profile is also linear. There is no internal heat generation. So internal heat generation means, suppose there can be nuclear fissions, and there can be other processes due to which there can be generation of heat within this material, within this plane wall, within this slab. Okay, so we will discuss it more brief manner in the upcoming lectures when we will derive the equations for the Cartesian coordinates of the heat conduction. Okay, so we will see that in more detail there. So for now we can just understand this internal heat generation is not there. That means Qg, heat generation, is 0. Okay, this Q is equal to capital Q over, you can say, volume, or it can be watt per meter cube. Okay, so this is Q. From here you can very easily understand the definition, right? Okay, the bounding surfaces are isothermal in character. The bounding surfaces are isothermal in character. I already told you. Isothermal means in this plane, throughout the plane, there will be no random temperature variation. Throughout the plane, the temperature will remain same. At this point, temperature T1, this point, temperature T1, this point, temperature T1, like this. The material is homogeneous and isotropic. Okay, homogeneous means that the properties are same. Okay, the properties are same of this material, and isotropic means that changes in direction cannot have any impact or have any domination over the different characteristics of the material. Okay, so this material, I am assuming that it is homogeneous. It is not heterogeneous. It is not anisotropic. It's isotropic. Okay, isotropic. The value of thermal conductivity is constant in all directions. The value of the thermal conductivity will be remaining constant in all directions. Like thermal conductivity, as we have already said, that K, thermal conductivity is small k, or in some cases, in some books, you will find that as lambda. That is equal to what? That is equal to watt per meter to degree Celsius. Okay, so I can say that this copper is having better thermal conductivity than that of wood, right? So you can understand that copper will be having better conductivity than that of wood, or like this we can have the comparison between different materials. That is why it can be also named as the thermophysical property of material. Okay. So some essential features of the Fourier law, like it is applicable to all matter, maybe solid, liquid, or gas, because we have seen that why it is applicable in liquid. If I hadn't aware you, if I didn't have the knowledge that it can also be applicable in the stationary fluid, and in the category of fluid you can get the gas as well as the liquids, right? So in case of stationary fluids, you can also have the conduction of heat. So in those cases, it is applicable to all the matters, but it should be homogeneous, it should be isotropic, right? And the flow of it should be unidirectional, and all the other assumptions that we have seen. Steady state condition should be there, right? Steady state means that it will have no variation with the time. Okay. It is applicable, it is based on experimental evidence and cannot be derived from the first principle, or general derivation is not there. It's a vector expression indicating the heat flow rate is the direction of the decreasing temperature and normal to an isotherm. Okay, it can very easily be understood. It helps define thermal conductivity of the medium through which heat is conducted.